Hi, and welcome to this video in which I hope to explain how my broadcast Sonic Pi Orchestra works. Now normally I would have about 8 computers running this, one master computer and 7 slaves, but it's very difficult to video that in a way where you can see the code. So I've actually reduced the orchestra to two computers because that can illustrate how the system works. And both of these are being displayed on the same screen here. This Sonic Pi is actually native to this iMac where I'm actually running, and over here we have screen sharing of my MacBook Pro, which is running the master copy or going to run the master programs for this. So we've got 2 machines, which is a mini orchestra if you like. And the one further thing we need is some means of connecting the two together, and that is going to utilize a Python script. So just one further feature before we continue with that. The way I'm doing this video is, as I say, screen sharing the MacBook Pro here. I'm taking the audio from that and I'm feeding it into the iMac via a USB audio interface, and then I'm using the program which is called Loopback, and that is going to take the output of Sonic Pi, the output of my internal microphone, the output of the Steinberg audio interface, which is taking the audio from the other Mac, and it's going to feed them all together, and I'm listening to that in my headphones, and it is also going to the recording software which I'm using to record this screen. So that's how we get around with that. And the other thing we need to look at is this block diagram here, which shows how the system works. That is the MacBook Pro here. That is the that's the MacBook Pro there, and you'll see that there's a second box here that says it's a Python script running on this computer, which I call Computer 1. And if we have a look at the code for that, we have a look at the code for that, which we can see if we go to here, and I come right down to the bottom and look at that. This is, perhaps if you haven't used Python before, maybe a slightly fearsome script, but the purpose of it is this. What we want to do is to talk to all the machines on the network, but we want to make it easy. We don't want to have to spend a lot of time typing in IP addresses so that we know where to send the data. So instead I decided to use the broadcast address. This is the address on your local network which ends with a 255 for the 4th section of the IP address. I'm using the local network 192.168.1, 0 up to 255. In this case, you might use 192.168.0, or maybe some of the other the other local address networks in yours. It doesn't really matter. Whichever one you use, the broadcast address we're going to use has got to end in 255 there. And this Python script is going to send all of the packets it sends out to that address, so it's not addressed specifically to any of the machines on the network, but they can all receive it. And it's addressing it to port 4560, which is the address at which Sonic Pi listens to incoming OSC messages. You can see incoming OSC port is 4560 there. So what does this little Python script do? Well, first of all, it runs a server which is going to listen on the local address for the machine it's running on, 127.0.0.1, and it's going to listen on port 8000, which is the one I use by default here, You can specify another one if you want, but that's what we're going to do. And so this receives messages addressed to 127.0.0.1 on the local machine to port 8000. And down here, there is what's called a dispatcher. And when we get an event saying that an OSC message has been received, and it is in particular, it is looking for an OSC message which is addressed to /trigger broadcast. It extracts the data from that, and I've allowed up to 10 items of data. That's just an arbitrary limit. In fact, I think I'm using 8, so there's just a couple of spare there. And it sends those items of data to a little function called broadcast, which is defined up at the top here. Here it is, broadcast, and it receives the arguments P1, P2, P3 up to P10. And what it does is that if the argument is missing, it says, okay, I'll just make it a 0 string. So if we just send an argument 1, 2, and 3, these would have numbers in them. The rest of them would just be ignored because they would have a null string. It then reconstitutes the message by saying, if there isn't an empty string there, then add it to the message we're going to send. And when it's done that, it sends out to the broadcast address a message which it addresses to /broadcast, and the message is just going to be a string of these numbers here. Now, I'm not going to go into more detail of that, but it is a similar program to one which I've used in lots of previous projects with SonicPi, which involve interfacing with other objects, for example, with the GPIO pins on a Raspberry Pi. But it is something which you can look at in more detail in your own time. So let's go back to our preview here. What happens is that the master computer sends out an OSC call to the local host, that's 127.0.0.1, port 8000. The Python script running on the same machine receives that message. It resends it to the broadcast address 192.168.1.255 on port 4560. And however many other machines we have, I'm showing 5 other machines here, these are all listening by default to the broadcast address, and on 4560 they will all receive that information simultaneously, and that's important because it means that they're going to be synchronized together with it. There is one other problem with audio latency, but we'll deal with that in a moment. And notice also it sends it back to the master machine, so it also receives the message at the same time as the other computers here, and so it will work in the same way in taking that information and using it to play a note, or as we'll see in some cases, play some percussion samples. So that's basically how the system works. You may say, well, why do we need the Python script? Why can't SonicPi send directly to these other machines? Well, the answer is that it is not enabled to send to broadcast messages, and so this is why we need to use this different Python script. And also, I think it means that it's easier to get the synchronization because everything is receiving at the same time from exactly the same system that's sending, and so any timing delays due to this are eradicated from that. So that's our picture. Let's now go and have a look at some software. Right, we've switched to look at the iMac screen, and this is one of the slave computers, if you like, which all have identical software on them apart from the first couple of lines. The first line here says computer equals 5. That's because this computer is normally the 5th one of the 8 that I have in my normal orchestra. And underneath it, it is adjusting the audio latency of this machine, and it's putting a delay of 234 milliseconds there. And that is because this is quite a fast machine, and therefore, in order for some of the slower machines to play in time with it, latency-wise that is, like a Pi 3B, which is also normally in my orchestra, that would have a much lower latency setting, so that effectively we're delaying the sound that comes out of this machine here so that it would play at the same time as my 3B. In fact, the latency setting for both of these two machines, they'll normally be the same, but I think in this particular case I've reduced the setting for the MacBook Pro because there's some additional latency introduced by the fact that the audio from that computer is going through another sound interface before it comes back in here, as I showed you in that loopback screen, and it's joined into the other video. So it's quite nice because you can make adjustments for this, and we'll see how this is done in the first program we're going to look at in a minute. The other thing is that different pieces of music will have different numbers of parts in them. Some of the pieces I have done have had up to 9 or 10 different parts, which you, and therefore in that particular case, you have to allocate more than one part to a particular computer. Some other pieces have only got, say, 4 parts, which with 8 machines mean that you can, if you want, allocate 2 parts to each computer. Rather like in an orchestra, for example, the first violin section, you might have up to 10 or 12 violins playing in a large orchestra, or maybe just 4 or 6 in a smaller one, and they are effectively, you hope, all playing the same part. And so we need to accommodate both of those because we don't want to have to spend ages fiddling around individually, having to alter the programs on 8 computers. If we can do it all in one of them, and the master computer is going to decide which machines play which part. All it needs to know is that when it sends the information out, if it knows the computer number it's sending it to, in this case 5, it can then allocate the correct parts to this. So when we start playing a piece, the first thing we do is to send it out so that the first item of data in the string of numbers which follow the initial /broadcast, the first item following that is normally going to specify the part that needs to be played, not necessarily the same as the computer number, but the first string that we send out, the first command that we sent out, is always going to have the number 99, just chosen arbitrarily, so that when we get a message coming in addressed to /broadcast and it syncs here, B is going to have in it the list of numbers which are sent, and it checks to see if the first one is 99. If it is, it's going to start working out what channels have to be played by this particular computer. Now let's just go and have a look at the sending side, and here is the sending program for this particular program, which is actually going to allow us to adjust the audio settings, and that is sent from the master machine to /trigger broadcast. Remember, this master machine is sending to the Python script, and that is then going to take the same numbers that follow this and send them out as a broadcast package, which would then be received by this one over here. So there's the 99, the first bit of data, and then along the top it tells you which computer numbers you're sending to. Computer number 1 is going to be asked to play the channel of data, which is channel 0. Computer number 2 is going to play channel 1. Computer number 3 is going to play channel 1. Computer number 4 is going to play channel 1. And just to show how it can be done, for computer number 5, I'm going to make that one play 5 channels. Channel 0, 1, 2, 3 and 4. And the way you do that is you put it inside speech marks and then inside square brackets as a list. The reason for the speech marks is that SonicPi at present can only send numbers or strings. It can send an integer or a number with a fractional part on it, floating point number, or it can send a string. It can't send a list directly, so it's going to send it as a string, and at the other end we're going to turn it back into a list. And then because I've got 8 ones, I'm just sending the other numbers, but there aren't actually the machines to respond to these ones, so these would actually be sent out, but nothing's going to respond to them. The first machine, which is the master one, is going to receive the 0, so it's going to know that it has to play data going to channel 0. The fifth machine that we're going to look at over here is going to receive information which is going to tell it has to play on 0, 1, 2, 3 and 4. So I think the best way to see how this decoding actually works is if I start this program running here and send it out, and it's going to be received at the same time. But I have to remember one thing before I do that, and that is that on this machine here we need to change to the terminal, and we need to start the Python script which I've called broadcastosc.py running. It's all set up here in a terminal window, and if I press the enter key, it starts running, and you'll see that it says that it's serving or listening to information coming in on the local host to port 8000, and it's broadcasting out again to 192.168.1.255 on port 4560, which is what we said. And so what I'm going to do is to start this running and stop it almost immediately. So start, stop. Now, if we look at, go back and look at the output of this, you can see that this has sent a broadcast message which contains 99.0111, and then inside square brackets as a string 01234 and then 111, and that was sent as we showed from here. There's the data it's sent, and it has been sent out, and at the other end it is actually being received here, and what it's going to do is to go around a little loop here, and it's going to decode the different items which were received, and those we can see here if we just scroll up a little bit so where I can see, there it is. There's the one which was received, 99.0111, then the 1234 and the 3 ones at the end. It's going to decode them, and it's going to take the integer parts, and it is going to turn them into lists of 1 entry, and you can see that that happens in this decode function here. We pass the first item. We're going to go around a little loop which is going to take each entry in the list B, which is this list here, and it's going to decode it, and it's then going to add the value it gets to another list that starts off 0 with nothing in it, called OP, and it's going to do that, and at the end of it it's going to print out what it's got. Well, in the decode script I've asked it to print the entry that it gets, and then it goes through the decoding process. If it is in a number, it's simply going to turn it into an array using the Ruby array brackets DL, and that just essentially puts it inside square brackets. So the first thing it looks at is 99, then the second one is the 0, then the 1. Now when it gets to here, what it has to do is to turn that into that, which is essentially to remove the quotation marks outside this and just take the contents of that. You do it in a slightly roundabout way. First of all, you take the entry here and you just take the numbers in it, 0, 1, 2, 3, 4, and you then turn it into a list of numbers which will be inside speech marks, and then you get rid of the speech marks and it's explained here in the text. It's going to take that and it's going to change it to that, and you can see the output there. And so now we've got this list, and now it knows that this is computer number 5. It takes the entry with index 5. That's entry 0, 1, 2, 3, 4, 5, and it stores that as the channels to which this computer has been asked to respond. Anything addressed to channel 0, 1, 2, 3 or 4, and there it is, it's printed out here. Channels for this computer are 0, 1, 2, 3, 4. So that's how it works. And then if we look just below this, I stopped the program almost immediately, but not before it had actually sent out the first bit of data, which is actually in a slightly different format. It's not one of these configuration screens. It starts off, and the first item data is the channel it's sending to, channel 0, and you'll notice that there are 2 machines which are going to respond to that. Machine number 1, which is the master computer over here, and also machine number 5. It can also respond to channels 1, 2, 3 and 4. There's nothing actually coming to those channels, but it's going to respond to that 0 there, and so it's going to receive this data. And what the data consists of is the following: the channel number, then it's the note you want it to play, the duration that note is to have, and then it has the value for, let me just see, for the next thing, let's look down to where it's actually sending it here. The next thing is going to be actually a number which is going to give the sustained value, which is 0.5 there, and the next one is the release value. And what it does when it plays these over here is it multiplies the duration, which is 1, by the sustain fraction, which is a half. So it's going to actually sustain for 0.5, and then it's going to release for a time of, where's the number? Down here, 0.2. That's just a rounding sort of error, 0.2. So it's going to release for 0.2. It's going to use the pluck synth, and it's going to be going at a rate of 120 beats per minute, and the volume is going to be 0.6 there. So that's just going to give a sharp note. I give quite a long sustain note because it is a percussive note, and it's actual, the ping will be much shorter than that, but it allows it to decay away slowly. So that's how that works. And if we start this playing again, you can see that both machines are playing at the same time. Now this program is normally set up to choose 2 machines at a time, so you can see that they're both playing at the same time. It only actually did 10 beeps before, because in the program there's a list there of 10 72s with the rest after it and 20 durations of 1. So it's got 1 second of 72, 1 second of a rest. And this is the routine which is going to send that. That sounds like broadcast OSC, channel 0, note, duration, scale factor for sustain, scale factor for release, synth, BPM, and the amplitude. That's just a QT is a scaling factor for how quiet you make it, so that you can adjust that just in a main calling program. And if you've got a list of things to be played, we'll see in a moment a playlist, something like this. At the top of that program, we set the attenuate factor to 0.6, and that means that every program in here will play at 60% of the value that's actually specified in the program. So if I wanted it very quiet, I could set that down to 0.1 or loud up to 1. It's actually a clamp between that range, 0 to 1. Okay, back to here again. So what I'm going to do is to change that to 100 there, and that to 200 there, and we're going to start this playing. And there's one other change I'm going to make, which is temporarily to remove, which line is it? That line there. Because I want to be able to rerun this program while it's running, and that would actually reset the channel if I didn't do that. So we'll just stop that and rerun it, and we'll start the programs both running again now. There we go. Now they're both playing at the same time, and if we start adjusting these, if I take the volume of this one right out, you can see that this is playing. Put its volume up as well. Take them both out, then neither is playing. This is the master computer playing, and remember its audio is being passed into this one, which is why you can hear it. And if I bring the other one up, make it very loud, they're both playing at exactly the same time, and so they are both together at exactly the same time. And in fact, the audio latency of this machine is set to 204 there. Again, it's normally set in a calling program so that you don't have to adjust all these individual ones. Initially it was in here up at the top here, but I commented it out so I could set it externally, and in fact you can see it's actually running with a different value. It's not 234, it's actually because I ran this program before I started recording first, and it was set in this case to 204. So that allows them both to work, and to show that it is that actually makes the difference, if I put this up to say 334 and rerun this, let's start this again. It's done its 100. We'll just start another 100 going. If we can get it so we can see both of those going at the same time, I will do if I do that. It goes higher up. You can see that it's not actually that one's running first. We'll make it up to say 400. Run it again. And we take it down to say 34. And run again. But when we go up to 234, it's right. So basically you run through pairs of machines at a time, and you can adjust the which ones are set to 0, and so that you can take any pair of machines at a time and adjust them. Then right at the end you can set all of these to 0, and you can have them all playing the same ping at the same time. So that's the end of the initialization, if you like, and that's all this particular program does. So we'll stop that one running again, and you can see that once we've set that, everything else decided as to which notes this machine will play is decided in the master program here. So there is no further initialization to do here. The reason for this line here that I commented out is that the first time you run this, if you didn't have that line set there, we would have 0 for the channels, and when we get into this down here, this line here would give an error and would stop the program running. Now, these programs will be made available, so I'm not going to say more about that, or we'll be here all night, but that gives you an idea of how that works. So let me now move back to the program here, and we'll actually play something that plays some music, so it's going to be slightly easier to hear. And in fact, there's one other program which we can play which will fit in here. Normally I run them using run file, because once you put a significant amount of music here, the programs get far too long for a SonicPi buffer. But there is one other program that will run here which demonstrates how the synchronization works very well. and that is a program which is called Scales. And so I'm going to load that one in here. There it is. It's called Scales, and what this does is that it's normally designed to be run on 8 computers, and what I've set for the configuration is that machine 1 is going to respond to channels 0, 2, 4 and 6, and machine number 5, which is here, is going to respond to channels 1, 3, 5 and 7. The other ones in between, just to space those out, machine 2 is going to respond to channel 9, that to channel 9, that to channel 9. No, there isn't a channel 9, so they won't do anything, even if they happen to be on my network. They're actually physically not on, so it wouldn't make any difference here. And what we've got is each channel here, there are 8 channels, which are called A1, A2, A3 up to A8. And channel A1 plays a C, then it has a lot of rests, then it plays another C. Channel 2 is going to play a D 1 beat later. Channel 3 is going to play an E 1 beat later, and so on until we've played an increasing scale, and then the scale is going to decrease back again down there, and we've got a total of 16 beats, and that plays the scale. We're going to play it at different speeds. The beats per minute are going to start at 390, and then they're going to go up to 300 and 500 and, no, 620 at the end. So the scale's going to get faster and faster. And this is how we actually broadcast these. We're going to do this 24 times. Each time we're going to make the speed increase, and we're going to send this information to channel 0 for the first one, channel A1 and B1, and it's going to have readings for the sustain fraction, release fraction, the synth, and then the BPM there. This is going to send a cue, which is going to be used later, to the function which is going to send this, because one of the things that made that this take quite a long time to develop was that I found that in order to get the timings right when you changed the tempo, it was very important that you didn't just put this in a loop and continue, because it started doing the change at the time before this had finished. And so what I do is I take the last one of these, and when that has actually finished playing, it will send a cue, and that will sync, and at that stage it'll go back and start the next rotation round that loop, and at that time it will change the value of I, and hence the value of the BPM that it's going to use. Let's just perhaps go and have a brief look at this routine. Here it is. You can see that sometimes it has notes which are going to play as chords, so this first little bit will deal with playing notes, sending out notes at the same time interval. Otherwise, it's going to send just a single note, and then it's going to rest, depending on the BPM, for the sleep duration of the corresponding durations of this list that it's sending here. And when it's finished all that, it sends the cue to say, I've finished, back down to the bottom. Well, that's a lot of verbiage. The proof of the pudding is in the eating. So let me just start this playing here. And it sounds like a scale. But if I take out one of the computers, take out the other one, this is only responding to channels 1, 3, 5 and 7. And that shows very well too how the channels increment together. And you can see it can really deal with very fast notes, no problem at all. 590, 600, 2 to go, 3 to go, 1 more to go after. That's the last one. Just run that again. notice down here you can see the cues, numbers changing. This is going to respond to anything where that number is 1, 3, 5 or 7, and this one is going to respond to anything where that number is 0, 2, 4 or 6. So they're playing alternate notes as we go through this. There we are. Okay, now as I say, once you get to some of the things which have got significant bits of music in them, if we look at this one, for example, it just happens to be here, you can see I've actually got 2 lines for OSC here. This is because this is what I normally use with 8 machines, playing 2 parts. To machine 1 and 2 are both playing channel 0, 3 and 4 both playing channel 1, 5 and 6, 2, and 7 and 8, 3. In this case, so that this could be played, if we wanted, on this setup, channels 0 and 1 are played in this machine, and channels 2 and 3 are played on channel 5. But you can see why we need to play, because we get quite a lot of notes on this, and those actually extend quite a bit off the page. There's a lot of data here, but the essential program is exactly the same. You play each one of these pairs in turn, and each time you change from one to the other, the tempo is going to change, and you have they're all sent to the BOSC routine, and that is going to change the notes that are played as we go through these lists, and at the end of it, it's going to send a cue which says I've finished that, and that can go back round, start the next one, and it will change the tempo, and these will all happen together. Now in fact, if we come to here, this is the way that this is normally done. I've got all the 16 pieces or so that I've so far prepared to use this system here, and I can comment out any of them. And the first one I've got here is a piece called Dancery. This is a series of dances, and these are all medieval stuff, so quite ancient. And when this is finished, again, we need to make sure that we wait till everything's totally finished before we go on to the next one. And so one of the other things is that the end of the program is set to send a cue, an OSC cue back to here, and it sends something saying play next, and the data of that is the name of the program that it's doing. And so it says stop this existing program playing if the value in that is equal to the value which is supplied to here. In this case it would be detect finished 0. So finished 0 is received from there, then it knows that this has got to stop, and it then sends a cue which is picked up here, sleeps for 2 seconds and starts the next one in the list. So that's the way as I get these all playing one after the other. So the first one, one reason I've done it is that it actually includes some percussion as well. And the way I deal with percussion, if we look at the Dancery script, which is this one here, is, and you'll notice that this has the same decode and live loop that the other programs have. The one over here, there's the live loop, there's the decode. It's exactly the same, except this one has got an extra bit added on the end. Dancery, where is it? Should have an extra bit added on. Yes, here we are. It also responds to a channel which is 20. Now that's not to go to another machine, that goes to this machine as well as any other ones. It always goes to this machine, 20, and it looks at the note which is being received, and if the note being received is an F sharp in octave 3, it's going to play a sample drum cymbal close at a rate of 1.05. It doesn't worry, use the sustained values which are there, it doesn't need them. If the note is a G3, it's going to play a high soft tom-tom at a rate 1.2. So we can play percussion like that. And if we look down at the bottom, the last channel in this is going to be sent, that's part 6, is going to be sent to channel 20. And the second last part is going to be sent to channel 20. This one is playing F sharp 3s, this one is playing G3s. The way I got these is that I actually took a standard MIDI drum part and pasted it into a different instrument, and that's the note that came out. And then I just changed the note into playing a suitable sample when it's received. So let's see what that sounds like. Here we go. There's the percussion. They start playing together. It's only part of this that I've selected. Take that out. Put that in. So both machines going nicely together. And it's exactly the same. If this, instead of playing parts 2 and 3, I can just play part 2 on one machine, part 3 on another machine. And in the same way, just play part 0 here and part 20 and part 1 on another machine. Or maybe even just part 20 on this machine and parts 0 and 1 on another. That's the end of that. Now watch what happens. It stops and it sends a function and it starts the next one, which is this one here. It's also got percussion. Get the master machine to print out what's being playing and the current tempo, and all the machines will say which channels they're listening to, which is useful for the debugging purposes and also knowing which one is which as you go and play. You can see the cues being received here, and if we go back to the script here, you can see them all being sent there. Rather nasty numbers because of rounding errors. I think the actual settings are 0.5 and 0.95 and 0.05 for those two values. And the volumes were probably, I got the value of 0.6 times whatever was set in the program. Really quite intricate rhythms you get in this. Victorious, I forget his dates, but it's something fairly early, 1500s or so. So we all know about having a groovy time even back in those times. When you get several machines playing, particularly with antiphonal music this way, you've got instruments playing and answering each other. It's really great to have your computers spread out around you. I usually have them in sort of semicircle around me, and then you get parts answering across on either side of you. You'll notice there's no pan settings in here because there's not really much point in trying to move when you're using this actual positioning of your speakers for the different machines to give you your audio pan spectrum. You could use this same technique for triggering live loops running on certain machines, just sending cues to start or stop. The basic mechanism of the broadcasts can be used and send individual channel information, which can do anything you want, to individual machines. You obviously have to have slightly different receiving screens. Now we go on to the next one. Notice the finished signal sent to channel 10 there, and then starting off on the next one. Frere Jacques, many parts. I'm going to get faster. Gone up to 320 now, the tempo. You can see on the screen down here. Slower again. Five instances, 3 played in one machine, 2 in another. Slower. Different synths, notice too. Pulse, blade, tri, saw, chip lead. Then I think we're going to hear the scales once again. Remember, 4 notes of the scale played on this one, 4 notes played on this one, and they're interleaved. It's quite a nice rhythm, that gives. See the different channels there. The final piece we're going to play is some early music played effectively with a guitar accompaniment. Commenting these out, show how you can change what is actually being played. So just a couple of things to before we finish. These videos will be quite useful if you actually want to use this yourselves, as the techniques of sort of setting it up and so on. As I say, normally the main machine is run from a playlist like this, and some important things: it sets the audio latency of the main machine here, because I've commented it out in all the individual programs. Secondly, it sets this attenuate value here. Again, that will assume a value of 1 if it's missing, but just to show how it works, here is a piece, the first one here, played with the attenuate set to 0.1, so it should be quite quiet. Oops. Sorry. Yes, it's the broadcast one there, and you can hear it's very quiet. And if we now set this up to 1, stop that playing and start it playing again, you can hear the difference there. So that hears it. That wasn't, I meant actually to do it on a slightly different one. Let's just have a look at this one here. And that was one of the ones in the video which I previously produced with the full orchestra. Well, I think probably you've listened to me for quite enough. I will be publishing these, and there will be a link below the video showing where you can get access to the programs. And if you have any comments, I welcome them below this, or on the in-thread SonicPi in-thread.sonicpi.net. So thank you very much for watching.